Cosmologists estimate that the acceleration began roughly 5 billion years ago. Before that, it is thought that the expansion was decelerating. Due to the attractive influence of matter, the density of dark matter in an expanding universe decreases more quickly than dark energy. And eventually the dark energy dominates. Specifically, when the volume of the universe doubles, the density of dark matter is halved. But the density of dark energy is nearly unchanged. It is exactly constant in the case of a cosmological constant. Projections into the future can differ radically for different models of dark energy. For a cosmological constant, or any other model that predicts that the acceleration will continue indefinitely, the ultimate result will be that galaxies outside the local group will have a line of sight velocity that continually increases with time, eventually far exceeding the speed of light. This is not a violation of special relativity because the notion of velocity used here is different from that of velocity in a local inertial frame of reference, which is still constrained to be less than the speed of light for any massive object. See uses of the proper distance for a discussion of the subtleties of defining any notion of relative velocity in cosmology. Because the Hubble parameter is decreasing with time, there can actually be cases where a galaxy that is receding from us faster than light does manage to emit a signal which reaches us eventually. However, because of the accelerating expansion, it is projected that most galaxies will eventually cross a type of cosmological event horizon where any light they emit past that point will never be able to reach us at any time in the infinite future because the light never reaches a point where its peculiar velocity toward us exceeds the expansion velocity away from us. These two notions of velocity are also discussed in uses of the proper distance. Assuming the dark energy is constant, a cosmological constant, the current distance to this cosmological event horizon is about 16 billion light-years, meaning that a signal from an event happening at present would eventually be able to reach us in the future if the event were less than 16 billion light-years away. But the signal would never reach us if the event were more than 16 billion light-years away. As galaxies approach the point of crossing this cosmological event horizon, the light from them will become more and more redshifted, to the point where the wavelength becomes too large to detect in practice and the galaxies appear to vanish completely. See Future of an Expanding Universe. Planet Earth, the Milky Way, and the local group of which the Milky Way is a part, would all remain virtually undisturbed as the rest of the universe recedes and disappears from view. In this scenario, the local group would ultimately suffer heat death, just as was hypothesized for the flat, matter-dominated universe before measurements of cosmic acceleration. There are other, more speculative ideas about the future of the universe. The phantom energy model of dark energy results in divergent expansion, which would imply that the effective force of dark energy continues growing until it dominates all other forces in the universe. Under this scenario, dark energy would ultimately tear apart all gravitationally bound structures, including galaxies and solar systems, and eventually overcome the electrical and nuclear forces to tear apart atoms themselves, ending the universe in a Big Rip. On the other hand, dark energy might dissipate with time or even become attractive. Such uncertainties leave open the possibility of gravity eventually prevailing and lead to a universe that contracts in on itself in a Big Crunch, or that there may even be a dark energy cycle, which implies a cyclic model of the universe in which every iteration, Big Bang then eventually a Big Crunch, takes about 1,012 years. While none of these are supported by observations, they are not ruled out.